Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tier. It's my continuing feature on the Math Lovers book. And I just started a new section of Chapter 6 on group theory yesterday. Now I'm talking about infinite groups. So I think for the rest of the chapter, the only groups I'm going to talk about now are infinite groups. And as we'll see, there's a lot of very important examples of infinite groups. Today I'm going to talk about another one, namely the 2D rotation group, which is given the notation SO2. It's just a group of rotations in a plane, if you like. Um, so the idea is that it's probably better to cut to the picture here. So if you just take any point in the plane, say x comma y, a point in the xy plane, you can rotate that point about the origin by a given angle theta. And if you do that, you get a new point, which I'm calling x prime comma y prime here. And you might wonder, how do you get x prime and y prime in terms of x and y? Well, I have the formulas on the top of this slide. X prime is x cosine theta plus minus y sine theta, and y prime is y x sine theta plus y cosine theta. Um, and I even show a derivation of these formulas in this picture. You can do it geometrically. It's a little bit complicated. I don't know if I want to go through all the steps here. Well, I might as well since I started talking about. Yeah. So look at x prime, y prime. So you can see there's sort of two rectangles in this picture. The first rectangle, they all have the lower left vertex at the origin, and they have two sides along the two coordinate axes, the x-axis and the y-axis. So you've got the red rectangle here with vertex x comma y on the upper right, and then you've got the blue rectangle with vertex x prime comma y prime, and x prime y prime is just what you get when you rotate x y by an angle theta. Well, let's just look at what's going on here. So how can we get x prime in terms of x? Well, x prime is just the value of along the x-axis where it intersects the origin. And how do I do this? Um, Notice that I gotta figure this out right myself. Is a little bit of a hard derivation, but yeah, maybe I don't want to derive this. Sorry about that. I changed my mind. You can do it yourself. Um, but it is true. You'll just have to take my word for it at this point. You can find this in a text on trigonometry, an undergraduate text on trigonometry. I remember when I first learned these transformation formulas for rotations. The derivation was very complicated. It turns out there's a much easier derivation in terms of Euler's equation, our e to the I theta equals cosine theta plus I sine theta. I don't want to get into that, but that's a better way to derive this formula, but you have to know some advanced math to do it. But anyway, so that's how you transform coordinates, and this set of transformations is a group. Why is it a group? Well, we let's call the element of this group, and I remember I said that I gave the name of this group SO2. The S stands for special, O stands for orthogonal. So this is a group of special orthogonal transformations of r squared, or if you like, the xy plane. And another way you could write this equation is as a matrix equation. I didn't do that here because I haven't talked about matrices. But SO2 is, just to cut to the chase here, I'm going to give you a little preview of what you can expect if you go further into this. SO2 is a set of 2 by 2 orthogonal matrices with determinant 1. You probably didn't even know what that meant. But you could write this matrix as a matrix cosine theta in the upper left, minus sine theta in the upper right, sine theta in the lower left, and cosine theta in the lower right. And this set of matrices of this form, where theta is an arbitrary real number, forms a group. And what sometimes we call this matrix R of theta. So in other words, this transformation is what I usually is written as capital R and theta in parentheses. And it turns out I didn't write this down here. I probably should have, but this is an additive group. So I mean, it's actually a multiplicative group because you're multiplying matrices. But it turns out that R of theta 1 times R of theta 2 is equal to R of theta 1 plus theta 2. So if you apply two rotations, and this shouldn't be a surprise, if you apply one rotation about an angle theta 1 and then you follow that by another rotation, and the angles are counterclockwise by convention. Counterclockwise means theta is positive. So if your first rotation was by counterclockwise rotation by an angle theta 1, and your second was a counterclockwise rotation by an angle theta 2, it turns out that the composition of those two rotations is just a single rotation, single counterclockwise rotation by the angle theta 1 plus theta 2. And that shouldn't come as a surprise because you know when you rotate something theta 1, you rotate an additional angle theta 2, those angles add. All that's saying is angles add. But another thing you should notice here, the angle is only really defined modulo 360 degrees, if you like 2 pi radians. This group is isomorphic to R mod 2 pi or R mod 360 degrees. I probably confused you by saying that, but it is an infinite group and it is a group. You can check that it satisfies all four axioms of group theory. It's not only associative, but it's commutative. The identity is just where you don't do anything. And the inverse is where the inverse of angle rotation by an angle theta is the rotation by an angle minus theta. In other words, the inverse of a rotation, a counterclockwise rotation by an angle theta is a clockwise rotation by an angle theta. That shouldn't come as a surprise because clockwise rotation by the same angle just undoes the first rotation. So that proves that this is a group. And the only other things I do in this section, in the subsection, is I give some examples. So it's good to be able to apply these formulas. Then you know how to transform coordinates of rotated points. So in the first example, we start with the point, what is it? 1 comma 0, and we're going to rotate by an angle of pi over 2 radians. That's 90 degrees. So we want to see how the point 1 comma 0 transforms when we rotate this point 90 degrees counterclockwise. And I think geometrically it's pretty easy to see what's happening because 1 comma 0 is just the point on the x-axis, a distance 1 from the origin. And I think you can see that if you rotate that point 90 degrees, it just sends that point to the y-axis. So you're going to get the point 0 comma 1. But we can actually apply these formulas to verify this. So let's just go back to the formula. So remember, x was 1 and y was 0. So you have x1 cosine, and theta is pi over 2. So we have 1 cosine pi over 2, but cosine pi over 2 is 0. And then you have minus 0 sine pi over 2. Well, 0 times anything is 0. So that shows that x prime is equal to 0, like we said. Similarly, y prime is now x sine pi over 2. X was 1, so we have 1 times the sine of pi over 2, but the sine of pi over 2 is 1. So now we're going to get 1 times 1, and now y was 0. So again, 0 times anything is 0, so we're going to get the point 0 comma 1. So that's how you do that. Pretty easy. Second example, I think, is a little bit harder. I have two examples that are kind of similar here. So in the, actually just the second example. In the second example, our initial point is x comma y equals 0 comma 2. So this would be a point now on the y-axis, the distance 2 units above the origin. And again, we're rotating by an angle, this time we're rotating by pi over 4. That's 45 degrees. So we're starting with a point 0 comma 2, which is 2 units above the origin. If you like, height of 2 along the y-axis. And we want to know what happens at that point when we rotate it 45 degrees counterclockwise. Well, I think you can see geometrically you're going to get a point in the in the second quadrant. That means that x is going to be negative and y is still going to be positive. But you might want to, wonder what the coordinates of that point is. Well, we can just plug in these formulas. Let me just do it here. Well, I can do it here actually. So, here our x is 0, y is 2, our theta is pi over 4. So we're going to get 0 cosine. For x, we get, I want to make sure I'm doing this right. Yeah, I bet you did the wrong example. Yeah, we get 0 cosine pi over 4 minus 2 sine pi over 4. Cosine and sine of pi over 4 are both equal to 1 over square root of 2. You can also write them as square root of 2 over 2. It's a little easier to write them as 1 over square root of 2 here. So for, remember, x was 0, so we get 0 times anything is 0. So the first term is going to give you 0, but then the second term is going to give you minus 2 divided by the square root of 2. That's going to be minus the square root of 2. So our x coordinate is going to be negative square root of 2. That's x prime. What about y prime? Well, we just apply the second formula. Y prime was x sine theta plus y cosine theta. X was 0, so the first term drops out. Second term is now plus 2 sine of pi over 4, but once again, sine of pi over 4 is 1 over square root of 2, so you're going to get 2 over square root of 2, which is square root of 2. So our point is going to be minus square root of 2 comma square root of 2. Those are coordinates at this point. And third and final example, I think this is the hardest one. Again, this time we're starting with a point on the x-axis. So we're starting with a point 2 comma 0. That means x is 2 and y is 0. And this time we're rotating counterclockwise by an angle of pi over 6. That's 30 degrees. So we want to know how this point transforms when we rotate it 30 degrees counterclockwise. Well, we do the same thing we did for the last two examples. The cosine, this time we have 2 cosine pi over 6 minus 0 sine pi over 6. We don't have to worry about the second term. But cosine of pi over 6 is square root of 3 over 2, I believe. So you're going to have 2 times square root of 3 over 2, which is square root of 3. So that's going to be our x prime, a little bit less than 2. Square root of 3 is about 1.73. Y prime is going to be x sine theta plus y cosine theta. X was 2. Sine of pi over 6 is 1/2. So we're going to get 2 times 1/2. Plus, and y is 0, so we can forget the second term. So we just get 2 times 1/2, which is 1. So the answer is 1. So that means that the coordinates of our transformed point are square root of 3 comma 1. Yeah, so that's how this point transforms. Anyway, that's how you do 2D rotations, and that's how you calculate the coordinates of the transformed points. So that concludes my video for today on 2D rotations, the group of 2D rotations. Thank you for watching. Long live math, and I'll see you guys next time. Bye.